talk about some common algorithms. Caesar Cipher. Yay. Bit of, ooh, that's small. That's small. Attributed to Julius Caesar, the basic idea here is just a alphabetic rotate to the right or to the left. The traditional is by 3 characters, so to encode your A's become B's, B, C, D, D's, and so on. And then to decode you say, okay, my D's become A's, and so on, and it loops around. So as I show here, your X becomes an A, and the inverse goes the other way. Very basic. In terms of what this looks like in software is when you have a byte value, like you're referring to AL or DL or BL, the low order byte of those respective registers, you see a add or a sub. And what that will do internally is that it will add that specific value or subtract that specific value, and essentially if it goes below 0 or above FF, it just rotates around because the carry is ignored. Everybody get that? Any questions on that? Okay. XOR and variations. Okay, I'm going to show an example here. So XOR, who remembers what XOR does? Where's my VM? There it is. Exclusive OR, yes. And what does exclusive OR do? Anybody, what does the exclusive OR do? Just give me kind of a high level.
Either but not both.
What?
Either but not both.
Either but not both. Oh, yeah.
Or parity.
Yeah, parity. The way I like thinking about it is if you're XORing, otherwise the result is not, yeah. If you're XORing with a if you have some value and you're XORing it with another value, that second value there, because we're doing the Intel syntax, the second value is going to be your masking that says these are the bits within that first value that I want you to flip. Because if it's a 0 in the initial, and it's a 1 in your masking values, it's going to flip it. And if it's a 1 in your initial and it's a 1 in the masking value, it's going to flip it. Okay, so.
Sorry, what was the password again?
For the VM?
Yeah.
No,
for the Malware.
Oh, hold on. Let me just show this to you first. Okay. So what we have here, I just loaded up malware.exe into IDA. What's the first thing maybe you notice, or one of the first things you notice? IDA, it finished the auto analysis. There's something missing. That's usually there. Graph mode, yay! Thank you, Corey. So usually you have a graph here. You don't have this listing. You have a little box over here that shows a little graph for the function that you're in. This is IDA basically saying, yeah, I don't know how to graph this function. There's something weird going on here. And this is the entry point for this. and you see there's this Saber :address. That's the section name that I have pulled out of the PE headers. So what's going on here is that there is something going on here. So that's just something to notice that kind of makes you go, huh, you know, what's going on? This is different than or opening a normal binary like we did in the previous class. But what we're interested in here is the encoding, and we maybe got some information from you know, somebody doing packet analysis or from some logs, and we say, I think maybe there's some kind of XOR encoding going on. So what you do is you have your binary open here, you do Alt-T to do a text search, and you type in there XOR, and you make sure find all occurrences is selected. Okay. What that does is it goes through doing a text search of the disassembly and gives you every line where XOR is. And if we had added a comment to one of the lines that says, this isn't XOR, you know, it would show up in here, but then it would also show the comment that says this is XOR. But since we haven't added any comments or anything, it's just showing all of the XOR instructions. This is a lot to go through. Actually, this isn't a lot compared to some binaries. Easiest method to start here, sort by instruction. Go to the top, and you see XOR, AL, AL. What happens when you XOR a register with itself?
Zeros out.
It zeroes out. It becomes 0. Yes. So we know that these syntax, that syntax is just a way to easily zero out a register. That's something that compilers will do. They'll use. You'll see this in regular binaries. So that's something we can just kind of ignore. XOR BL with DL. Well, maybe something's going on there. Maybe not. BL, DL, all these. And we see this XOR EAX with this 4-byte value. Huh, I wonder what's going on there. I'll take a look at that. And what do you see?
Graph.
You see a graph.
Thick line.
A thick line, yes. We see a bold line, which means what? There's a loop. I'm so proud of you guys. Okay. So there's a loop going on here. You see this XOR within this loop. Now what we don't see is necessarily a reading from memory. We see, okay, it's doing some with EAX, dec ESI, jump not 0, so ESI must be a, oh, move ESI 8. So this looks like a, what does this look like? What kind of loop? That we covered in the last class. Starts with an F, ends with an R. It's a for loop. Where your initial value ESI starts off at 8, instead of incremented, gets decremented, and you jump out when it's 0, or you continue jumping while it's not 0. But what we're not seeing is a reading into EAX. Seeing accessing AL, but not reading into EAX. So part of this, though, is that there's another, this is just an inner, there's another for loop. If we take a look up here, we see, oh, move ECX into EAX. Oh, what's going on down here? Oh, move EAX into EDX. So there is a moving in to memory and a incrementing of that memory location. So it looks like there's some kind of deobfuscation or decoding routine going on here. And what we can do is go through and pseudocode it and figure out what's going on. Something else we can do is we can go, okay, take a look at this. What are the cross-references? There's just one. Let me take a look at that. Huh, it's being called right after this weird string is pushed onto the stack. That's a good indication that's a decoding loop right there. So that's one way to find it. If you think it's an XOR, as I said, do a text search, Alt-T, XOR, find all, and then make sure that you sort by the instruction. So as everybody give that a try, what you're going to use is let me bring this up. What you're going to use is in the reverse engineering of malware folder, there's a labs folder. And in there is 4A, this is it. You're going to grab the file in there and extract it out to your desktop. The password for that is infected, all lowercase. Okay, let's go over msnsv.dll. Folks online get the answer to question 1, which function contains XOR loop? 100B. Let's go take a look. Oh, wrong one. Oh, hey, here. Okay, now I'm in malware. So malware. Just as a quick rule of thumb, a good way to help keep yourself from accidentally infecting yourself is to rename any exe to ex underscore. Still lets you load it up in IDA without issue, still lets you analyze it without issue. Just keeps you from accidentally double clicking on it. Okay, so where's that malware? There we go. Labs, MSP, we'll copy that here. It's going to get crowded. Okay. And we will take a look at that in IDA. Okay. Hey, we got a pretty graph. We got a graph. That must mean everything's okay. Okay, so text, XOR, find all. It's already there since I just did it. Sort. We go up to the guy and we see, oh, look at that. Let's take a look at this. We see an XOR with a bold line, good indicator, and that is 100B. Yep. That looks like that is where we are, XOR loop. Because we're reading from memory, arg0 to EAX, EAX, EDX, XOR, increment EDX. So what's going on here? Who can tell me what this loop is doing? And how it's different from just a simple read from memory, XOR it, right back to memory. Okay, what's this first one doing? Move. No, let's start here. What's that first one doing? Nothing. What's this next one doing? What's this move? What's it putting into EAX? What does that mean?
The first argument and function.
Yeah, that's the first argument passed to the function. So it's taking the first argument, putting it into EAX. Then what's this doing? let's move BL7. John, let's move BL7
Page 7, do 1.
into,
Another one on that.
no, that's an L.
Oh, no.
Yeah,
Page 7, yeah.
yeah. And what's BL?
It's not always, I know the
Yeah, that's the low order byte of BDX. That's a shorthand for the low order byte of BDX. BL is B, low order byte. You'll see that shorthand here, AL for the low order byte of EAX. This is important to remember for encodings. When you do single byte per byte encodings, you'll see references to just the low order byte of registers all over the place. Really good to know. So moving 7 into that. Okay, what's this? What's Leia doing?
So the stuff that's at the location of EDX plus EAX and ECX.
Close. Is it loading the stuff that's at the location of EDX?
In other words, it's taking the content of EDX, adding it to EAX, and the memory location that's at that summation, it puts in the ECX.
Yeah, basically. What this is doing is, because it's Leia, you can almost ignore the brackets. It's getting EDX plus EAX and storing it into ECX.
Yeah, but EDX 0 and EAX is the pointer that you specified X0.
Mm-hmm. Right. So if EAX is a pointer to a string or a buffer, although we know it's a pointer to a string because we took a look at where it was being called. Oh, different program. My bad. But right beforehand, there's a read file. So it looks like it's probably doing something with file. But this looks like some kind of offset syntax, especially since EDX is being incremented down here. So yeah, it's taking the EAX plus EDX, storing it in ECX, which then gets referenced down here when we move into. So then what are we doing? Move DL into AL. What's DL?
By EDX.
Low order byte of EDX? Yep. Another way of saying that is DL is EDX mod 256. And moving that into AL. What's this IMUL? IMUL BL. Where does it store the result of that? It's doing a multiply. I'll give you that much. Where is it storing the result of the multiply? That was a good one. Anyone online, where is it storing the result of the multiply? EAX. Yes. Stores the result of the multiply in EAX and uses the full register, EAX. So BL is 7, and it takes AL, which it got from DL, multiplies it by 7, does an XOR, and stores that in EAX. Does an XOR of the low order byte of EAX with the byte pointed to by ECX, which we got from here. So what this is doing, instead of doing a straight on just XOR, it's doing a incrementing XOR. by 7. Because the first time through, EDX will be 0. Will it be 0? Yes, EDX will be 0. So that'll be 0. So that'll be 0. So the result will be 0. Multiply it by 0. Next time through, EDX is 1. So that's 1. So that's 1. So when you multiply 1 by 7, you now have 7. Next time through, it'll be 2. So that'll be 2 times 7, or 14. Next time through, that'll be 3. So it increments the first byte with 0, the next byte with 7, the next byte with 14, the next byte with 21 hex, or corresponding byte representation. This is one of those things that you'll see. This is real malware we're dealing with, by the way. Anything that doesn't say lab such and such, this is real malware. So this is stuff that you will see in the wild, and being able to go through and say, oh, this is what's going on, and pseudo-code it out and go, there's a loop, there's our starting, I equals 0, I plus plus, here's our condition here to stay in the loop, and this is what's going on. That will help determine how you can decode that buffer or that string that's being passed to this without having to run it and infecting your VM. Any questions on that? This XOR loop. And something I did to maybe help visualize here is I pseudocoded it. We have our increment and indexing variable seems to be EDX, just set to 0 beforehand. So what I did was I just said, okay, that's I. So set to 0, we know it gets incremented each time through the loop, I++, and we keep going while it is, let's compare down here, less than arg4. And then I took a look in here and I said, okay, the masking value here is going to end up being equal to our index, because we have the DL there, mod 256 times 7, the IML here. And then we're going to take the low order byte of that. We're going to XOR it with the byte at our input string at offset, the index value. So that's how I would go about pseudocoding that. And based on this, you could maybe, this is being used to close the door there. Thanks, Drew. If this is being used, say, for obfuscating a file or deobfuscating a file, you could code this up in Python, Perl, Scheme, whatever you're most comfortable with, and run that and deobfuscate the file and then see what the contents are. Yay, pseudocode. Okay. So, where were we? We talked about that, XOR and variations. So that is real malware right there. That is something that real malware has done, that variation on an XOR, where it's incremental XOR. I've seen a simple, 1 value incrementing XOR, where the first one XOR was 0, and XOR was 1, and XOR was 2. This one just happened to go by 7. But this is real malware that you're seeing. This is what real malware does. Okay.